In this video, we're going to look at the differences between speed and velocity, along with a few examples of how to calculate them. This is a continuation of the previous video on distance and displacement, so if you haven't already checked that out, then please do so using the link above. For those who don't know me, my name is Chris Iannazzoni. I've been tutoring for about 2 years now, and I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. Position and velocity are directly related to each other. In fact, velocity is specifically defined as the rate of change of position. Using derivative notation, you could describe this as dx on dt, or simply just x dash of t if you use function notation. Simply put, as long as you know the position equation of your particle, then you can also find its velocity equation by simply finding the derivative of the position. In this example, our position equation is just a quadratic. If we want to find the velocity equation from this, all we're going to do is find the derivative of our quadratic. For example, if I want to know the velocity 3 seconds into the journey, then all I'm going to do is sub in t equals 3 into my velocity equation. And that's going to give us a velocity of 6 meters per second. We could even graph the velocity equation if you wanted to. Positive velocity is always interpreted as moving towards the right. So if we look at our graph of velocity, we can interpret this as saying that the speed is increasing over time at a constant rate, because the speed values are increasing as time moves on. If you want to be even more accurate with how you describe this, you could say that the particle is accelerating at a constant rate of 2 meters per second squared, but we'll talk about that in more detail in a later video. You don't even necessarily need to know the position equation to find velocity. Consider this case here where we have a position graph that is made purely of linear components. If the velocity is just the change in position divided by the change in time, then all we have to do to find the velocity for each given journey is find the rise over run of that journey, since it's linear. Looking at the first section of the journey, we see that we have a rise of 6 and a run of 3. That's going to give us a velocity of 2 meters per second. We can do this for the other 2 sections as well. The second section has no rise and it runs for 7 seconds, so the net velocity there is going to be 0 meters per second. And finally, the last section actually returns to the origin. Hence we say that the rise is going to be negative 6 meters because it's going back towards the origin. And since this was done over 6 seconds, we can say that the velocity for that portion of the journey is going to be negative 1 meters per second. We can then use that information to create our velocity graph. It's just going to be a bunch of horizontal lines at those particular values because the velocity was constant at those spots. We should also notice that the velocity graph is discontinuous, and this is a result of the sharp transitions of the position graph. We covered this in an earlier video on limits and continuity. We knew that if the original function was smooth, then the derivative function would have to be continuous. Lastly, we should consider how to actually interpret this type of graph. One such sequence to describe the motion would be as follows. The particle starts at the origin and then moves to the right at a constant velocity of 2 meters per second, and it does so for 3 seconds. So we've hit 3 components there. We've talked about its position, its velocity, and the time duration for that interval. The particle then remains stationary for a further 7 seconds. Again, we're hitting position by saying it's stationary. We're also saying velocity because again, it's stationary, and we're talking about the duration. Then the particle moves left towards the origin at a velocity of 1 meter per second, upon which it arrives at the origin after 6 seconds. One thing I'll clarify about that last bit is the reason why I didn't use a negative sign on the velocity, and that's simply because I said it is moving left. If you say your particle is moving in a particular direction, you don't have to put a sign on your velocity. In fact, you shouldn't put a sign on your velocity. Just like how there are differences between distance and displacement, there are also differences between speed and velocity. The difference is a little bit nicer. Speed uses distance for its equation. In this case, we're often calculating the average speed. When calculating the average speed, you simply want to know the total distance traveled and then divide that by the total time it took. Velocity, however, is going to use position for its equation. So if you want to know the average velocity over a given time interval, then you want to find the change in position and then divide that by the time duration. Depending on if your graph has turning points or not, speed and velocity might very well be the same thing. This is because velocity and speed are using distance and position as part of their equation. So the rules for position and distance also come through when it comes to calculating velocities and speeds. We'll look at a few examples for both. In this case, we're looking to calculate the average velocity over the first 5 seconds. To find velocity, we need to figure out our displacement. So all we're going to do is find the position at the start of the journey and then subtract that from the position at the end of the journey, giving us a net displacement of -5 meters. Now, if we want to convert that to a velocity, all we're going to do is divide by the time interval that it took, which in this case is 5 seconds, giving us a velocity of -1 meters per second. A negative velocity means that you're traveling to the left. Hence, we can interpret this by saying the average velocity for the journey was 1 meter per second to the left. Let's try the same example, but this time we'll calculate speed. If you want to find the speed, then what we need is the distance. So, if you want to find distance, then now we have to consider turning points in our position graph, because turning points indicate that the particle has changed directions. It's gone some distance in the positive direction and then gone back in the negative direction. To account for this, we're going to calculate our position in two separate parts. The first part is going to be from the start to the turning point. Basically, all we're going to be doing here is subbing in t equals 0 and t equals 3. Just remember that we're going to knock off that negative sign because distance can only be positive. Now that we have that, we're just going to calculate the second distance, which is going to be from turning point to the end, or in this case, between t equals 3 and t equals 5. All we do from here is add those two components together, giving us a total distance traveled of 13 meters. From here, if you want to convert that to a speed, you're once again going to divide by the time duration it took, which in this case means dividing by 5. And just like that, you have the average speed for the journey. If there are no turning points in your position graph, then it means that the particle has gone in the same direction for the entire journey. Under these circumstances, distance and displacement will be the same thing. To highlight this, we're going to use the exact same equation as before, but this time we're going to limit our domain to t equals 2, which is just before the turning point. Starting with displacement, not much is going to change here. We're just going to end at t equals 2 instead of t equals 5. Then, converting that to a velocity is just a matter of, once again, dividing by the time interval, which in this case is only going to be 2 seconds, giving us a velocity of -4 meters per second. Now, when it comes to calculating distance, we would normally have to look for turning points. But in this case, there are no turning points in our interval. So distance is going to be calculated the exact same way that displacement is calculated. All we have to do is make sure that we knock off that negative sign because, once again, distance cannot be negative. So converting that to a speed is once again going to be a matter of dividing by that time interval, which is just 2 seconds, giving us a speed of 4 meters per second. So you'll notice that the only difference between the speed and velocity is that speed has to be positive. Before we conclude, I just want to make clear the differences between when you would use what equation, because I've noticed that students tend to struggle here whether to use the velocity equation for your calculation or whether to use the position equation for your calculation. So here's the rule. If you want to find velocity at a specific time, then you would use the velocity equation. That's the purpose of the velocity equation. It will tell you the velocity for any given value of time. If you want to find the average velocity, then you have to use the displacement or position equation. This is because when you find averages, you're basically finding the slope over a given interval. And whenever you find the slope of position, you get velocity. If you try to find the slope of velocity, you would actually get acceleration, which is not something that we want yet. But we will look at that in the next video. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.